let's do this. 2xy minus x equals 3y plus 2. This should be actually a little bit nicer example. But let's see what we get. d dx of 2xy minus x equals d dx of 3y plus 2. d dx of 2xy minus d dx of x equals d dx of 3y plus d dx of 2. What this has, that the cosine example did not have, is the product rule. So a little bit more going on with this. Not something we haven't done yet this hour, but a little bit something different. To find the derivative of 2xy, I could do a couple things. I could yank the 2 out in front. 2 is a constant, so you could pass it through the d dx notation, and we could say this is simply 2 times d dx of xy. But then we have to keep track of the parentheses around that expression and then eventually distribute the 2 across the parentheses, and I don't want to do that. So I'm going to treat the 2x as one expression and the y as another, and I was to think of it as the product of those two expressions. If you wanted to, you could dissociate the 2 with the y, but that's what I want to do. Got to do something with the 2, and that's what I'm choosing to do with it. So it's the first times the derivative of the second plus the second times the derivative of the first, product rule, minus the derivative of x, d dx of x, that's 1, equals d dx of 3y. Well, in that case, it'd probably be nice to take the 3 and drag it through the d dx notation, because it would be 3 times the derivative of y with respect to x, but that's 3 dy dx. d dx of 2? 0. So plus 0 or just ignore it. 2x dy dx plus y times 2 minus 1 equals 3 dy dx. Get the dy dx's together on the left-hand side, and it will look like this. 2x dy dx minus 3 dy dx. What's the other side of the equation going to look like? Either 1 minus 2y or negative 2y plus 1, whichever you prefer. I think I might prefer 1 minus 2y, but ask me again on another day and I might prefer negative 2y plus 1. So I'm going to go with that. Factor the dy dx out of each expression on the left, and it'll be 2x minus 3 times dy dx equals 1 minus 2y. And dy dx then equals 1 minus 2y over 2x minus 3. So if we could find a point on this graph, we could substitute the coordinates into 1 minus 2y over 2x minus 3, and it would give us the slope of the tangent line. All right. So this is the graph. It actually did define a function. We didn't go to the trouble of finding it, but it turns out that if you take this equation and solve it for y in terms of x, you get y equals x plus 2 over 2x minus 3. So it does define a function, and the graph looks like that. And what I've done is had a and b represent the x and y coordinates of this point, and then over here m is that expression 1 minus 2b over 2a minus 3. Is that what we got? 1 minus 2y over 2x minus 3. So m is going to be what you get when you take the x and y coordinates of this point and you substitute them into that expression. Well, if it's just off here somewhere, who knows what could be meant by the slope of that tangent line, but if it's a point on the curve, it's the slope of the tangent line. Slope of the tangent line. So right there, or over there, anywhere on the curve, down here, it's going to be the slope of the tangent line. What's the significance if it's out here somewhere? Well, there might be various different ways to interpret that. Really not much as far as this function is concerned, but consider this. Remember we did the circle and said suppose it had been not a radius of 5, but a radius of 4 or 3 or 2. Basically, we had a family of circles, all centered at the origin. Well, there's a constant that we ran into when we were taking this derivative, and the constant was right there, ddx of 2. What if I change that 2 to something else? Not going to have any impact on the derivative, but it's going to change the original function. Basically here, we could change this number. Where it showed up in the original was right. Let's see, if we take this and solve it for y, there are a couple of 2's, I want to make sure I get the right one. I believe it ends up right there. I believe that's where that 2 ends up. Yes, it does. If we change that 2 to something, we get a different graph, but somehow our expression should still work as the slope of the tangent line. So consider this. What we have here is the graph of f of x equals x plus 2 over 2x minus 3. If we say, what if we say g of x equals x plus 5 over 2x minus 3? Well, that tweaks it a little bit, but if we move this point onto the green graph, if it's on that graph, it's the slope of the tangent line. We could do another one, change the 2 to an 8, and that gives us that curve. If we take that point, out here it doesn't mean much, but if it's on that curve, it's the slope of the tangent line. If it's on the curve over here, it's the slope of the tangent line. Or we could do, I had one more, but then there's a nice way where, try it sometime, you can define a sequence of whatever you want, sequence of points, sequence of curves, and so I just did a bunch of them, whole family of curves, and all I'm doing each time is changing that number, this expression we have for the derivative, if it's on any one of these curves, where it is, it's the slope of the tangent line for this entire family of curves. Now when you study differential equations, you get a little bit more out of that, and you can take it a little bit further. But I think as far as the expression having meaning, when we move the point off the curve, well, maybe we're moving it onto another curve where it's also the derivative of that expression, or at least